till now we have seen three kinds of unsymmetrical shunt faults on an otherwise balanced network. We have seen single line to ground fault, double line fault and double line to ground fault in a power system with fault impedance included. Now in my lecture number 111, I have told that the negative sequence reactance of a synchronous machine can be measured using this experiment apparatus. In this, what I have done, I have put a wattmeter with potential coil between VA and VB and the current coil in the line IB. Okay. And this voltmeter is measuring VBA. This dot signifies the polarity. Although we can change the connections or terminals of the connection if any of the needle or meter is giving negative reading. Similarly, this ammeter is reading IB. Now, we have to prove, as I have already told in lecture number 111, that this negative sequence reactance is equal to 1 by root 3 into voltmeter reading divided by ammeter reading into wattmeter reading divided by voltmeter reading into ammeter reading. Now, let us see how to prove this thing. Now, we know that this voltmeter is measuring, its reading is measuring VBA. It is nothing but VB minus of VA. Okay. Now, we will write VB and VA in terms of sequence components. So, it is VB1 is equal to A square VA1 and VB2 is equal to A VA2 and VB0 is equal to VA0. Similarly, this VA is equal to VA1 plus VA2 plus VA0. So, VBA is equal to A square minus 1 VA1 plus A minus 1 VA2. Now, using the equation VB is equal to VC, you can see clearly that from this circuit VB is equal to VC. I can easily prove that VA1 is equal to VA2 is equal to 1 by 3 VA minus VB. Okay. So, we can easily write VA2 in place of VA1. This relation we have already proved in our previous lecture. Okay. So, let me replace VA1 with VA2 since we need to find X2, so we will need VA2 as well as IA2. Okay, so VBA can be written as A squared minus 1 plus A minus 1 VA2. Now this A square plus A is equal to minus 1. So minus 1 minus 1 minus 1 it equals to minus 3 VA2. Okay, now we have got that VBA, the voltmeter reading, is equal to minus 3 VA2. Now we need to find what does this ammeter reads. Now this ammeter reads IB. Okay. Now if I somehow convert this IB into IA2, then we will get some relation to find this X2. So what we will do, we will try to write IA2. It is equal to 1 by 3 IA plus AIB, A square IB plus AIC. Okay. Now IB is equal to minus IC. From this circuit we can clearly see that IB is equal to minus IC and IA is equal to 0. So this is equal to 0 and IC is equal to minus IB. So we can clearly see that IA2 is equal to A square minus A IB. Now we know that A square minus A can be written as minus j root 3. How? We can clearly see that if it is 1, then a square comes here and a comes here. So minus a will come here. So their resultant will come like this. If it is 1, then it is root 3 and the angle is minus 90 degree. So this thing is minus j root 3 IB. Okay. So we can clearly see that IB is equal to IA2 minus j root 3. Okay. If I take j on the numerator, it will become j by root 3 IA2. Okay. So this is the relation which I have got here. So voltmeter reading divided by the ammeter reading and it is divided by root 3. What does it give? It gives minus 3 VA2 over j IA2 by root 3. Okay. So this is something which we have got here. Now this VA2 over IA2, it is nothing but the negative sequence impedance. Okay. If I want to write Z2 as Z2 angle theta 2, okay, I will write it as like this. Now here I have missed this 3 factor. That's why I was thinking that something is wrong. Okay, this 3 factor is missing. I missed this. So this root 3 will come into the denominator now. Okay, and this root 3 will come in the numerator now. Okay, so VA2 over IA2 is equal to Z2 angle theta 2 and this becomes this is root 3 here. So this root 3 will cancel this 3. It is minus 1 by j. Now minus 1 by j is equal to j only. I will take this into numerator. So it will become plus j. So I can see that voltmeter reading divided by ammeter reading into 1 by root 3 is equal to Z2 angle theta 2 into j. So I can write it as Z2 angle 90 plus theta 2. Okay, so we have got one of this relation and this is nothing but VBA over IB root 3. Okay, so from here we can clearly see that the angle between VBA and IB is 90 plus theta 2. Okay, that is angle between VBA and IB is 90 plus theta 2. This we can see from this relation. Okay, we should remember this because it will be utilized in the next step. Now we will carry on with the further steps in the next slide. Now let us see what is the value of wattmeter reading. The wattmeter reads, it reads the value of voltage between the voltage coil into, it can either be VAB or VBA. We don't want to even, let us say, show this dot because we can easily see, we can easily convert or invert the terminal connection according to the deflection of the needle. Okay, so let us say it is either VAB or VBA. The current in the current coil, this coil, and the cos of angle between this value, this input and the current input. Now from this example we have seen, if this let us say this wattmeter coil is measuring VBA, let us say we are assuming this case now that it is measuring VBA. Okay, so we can easily see that the angle between the parameter read by this potential coil and the current coil, the angle between them is 90 plus theta 2. Okay, so up till this point we have got this value. Okay, now if I divide this thing, voltmeter reading and the ammeter reading, their product, if I divide the reading of wattmeter by this product, what I will get? VBA into IB. Okay, so this will get cancelled out. So only thing remaining is cos 90 plus theta 2, and depending upon the deflection of this needle, this can be either minus or plus. Okay, so let us say I am taking minus sign here depending upon the deflection. Okay, so it will be minus sine theta 2, or minus minus, if I am taking minus sign first, let us say this VAB, it was there VAB and it is VBA, then it will be minus sign, so it will be minus minus plus, so it will be sine theta 2. Okay, so up to this point we have got the value of this part. This is sine theta 2. Now this we have already got. What is this? Z2. Okay, so Z2 into sine theta 2. If I take only the, let us say, the ratio of the magnitudes only, because these voltmeter and ammeter are not going to show the phase angle, they are going to show the magnitude only. So this will be VBA over IB root 3 and it will be only the magnitude of this term, which is nothing but Z2. Okay, so I will multiply this Z2 by sine theta 2. So now Z2 sine theta 2, what it is? We can easily see that Z2 is written as Z2 angle theta 2, which is Z2 cos theta 2 plus j Z2 sine theta 2, or it is equal to R2 plus jx2. So this Z2 sine theta 2 is nothing but x2 here. So in this way I have proved that this thing is going to give me x2, that is the negative sequence reactance of this synchronous machine. In this way we have proved that this apparatus or this experiment, even if I run this in steady state after the fault, it is going to give me the negative sequence reactance of the synchronous machine. Now in the next slide we will prove that in one of these scenario, single line to ground fault can be more severe as compared to a three-phase fault on the system. Let us see what is that scenario in the next slide. Now let us take a case that there is a synchronous generator which is solidly grounded. Okay. Now let us take first the case when there is a three-phase fault on the terminals of this generator. So these three terminals get short circuited in the three-phase fault. They can either now connect to ground or may not connect to ground, because if it is purely symmetrical circuit, then there will be no current here. Okay. Now you can see from normal network analysis also that the current flowing during the fault will be given by E over the transient or subtransient reactance, whatever we want to get during that duration. So let us say it is the subtransient reactance. Okay. So the fault current will be the per phase voltage developed, okay, in the synchronous machine divided by the subtransient reactance of the machine. So this is the fault current in three-phase fault. Because it is a balanced circuit, then this point and this point can either be thought of as connected or these can be thought of as on the same potential. Okay. So we have done this calculation on per phase basis. Okay. Now let us take a case that instead of three-phase fault, this generator has got a single line to ground fault, that is phase A has got a fault. Now we know that for a single line to ground fault, IA0 is equal to IA1 is equal to IA2 is equal to I fault by 3 is equal to voltage on that point before the fault divided by Z1 plus Z2 plus Z0. Now for this synchronous machine, Z1, Z2, Z0 will be replaced by, if we neglect the resistance part, X1, X2, X0. So the fault current in the single line to ground fault will be 3 times E X1 plus X2 plus X0. Okay. Now from equation 1 we can see that three-phase fault current is E over X double dash, and for single line to ground fault the fault current is 3E divided by X1 plus X2 plus X0. Now X1 is actually X double dash only. If I want to compare the current during the subtransient part, then this is X double dash. Similarly, this X2 is also, let us say, equal to X double dash if we take a cylindrical machine. Okay. And X0 is smaller than X double dash. That we have seen in our lecture number 111 also, that is lecture number 111. Okay. Now 3 times of fault current during three-phase fault will be given by 3E over X double dash. Or if I, let us say, divide this also by 3 just to see the comparison. So 3 times of IF 3 by 3 phase fault divided by 3 is equal to 3E divided by 3X double dash. Okay. Now this thing is smaller than 3E X double dash plus X naught, because X double dash plus X double dash plus X double dash is equal to 3X double dash, but this thing is equal to just X double dash plus X double dash plus x naught, which is actually smaller than x double dash. So this quantity is actually smaller than 3x double dash. So if this quantity is smaller than 3x double dash, then this current will be greater than this current, the current during the three-phase fault. So from the comparison of equation number 2 and 1, and from this relation, we can clearly see that the current in the fault during single line to ground fault is greater than the three-phase fault current on the terminal of a solidly grounded synchronous generator which is star connected. Okay, so in this way we have proved that there can be a scenario in which single line to ground fault can be more severe as compared to three-phase fault. Okay, so there can be various kinds of conceptual questions based on these topics which we have studied in our previous lectures on the unsymmetrical faults, and I have tried to cover a very typical kind of example in this so that we can build our concept. So if required, we will also try to solve 1 or 2 numericals in upcoming lectures. If you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.